Let us start this lecture with a thought process from Abraham Lincoln. Towering genius disdains a beaten path. It seeks regions hitherto unexplored, but unfortunately we always take a path which is easier, that means taken by others. And let us recall what we learned in the last lecture. We basically looked at about the equilibrium constants, right? And equilibrium constant from the reaction rate point of view by invoking the law of mass action. But now we will have to look at from the thermodynamics point of view how to determine the equilibrium constant and what is its meaning, right? Because we need to determine the state of chemical equilibrium, right? For that we will have to find out what is the direction in which the chemical reaction is proceeding, right? Or what is the percentage of extent of reaction is taking place, right? And for that we will have to invoke the second law of thermodynamics, because second law of thermodynamics indicates the direction which the process will be proceeding, right? And we know the second law of thermodynamics for a system, that is change in entropy will be greater than equal to dq by T, right? And of course, if it is a reversible process, that will be change in entropy is equal to dq by T. If it is irreversible process, it will be greater, right? And that is the principle what is known as the increase in entropy principle. That means the chemical reaction will be proceeding in the direction of increasing entropy. If it is decreasing, then it will not proceed, right? So, if you want to look at, for an adiabatic system, right, because in the chemical reactions which will be taking place, right, will it be adiabatic system or non-adiabatic system? For the chemical reactions, will you consider adiabatic? Right, you won't. There will be some heat will be going out. But however, for adiabatic system dq will be 0. So, therefore, the change in entropy will be greater than equal to 0, right, because dq is 0 na. See, if it is for adiabatic process, delta q will be 0, right. So, therefore, change in entropy will be greater than equal to 0. Now, if you look at that in a pictorially, see, change in entropy is increasing, that means the equilibrium will be achieved wherever there is a no change in entropy is equal to 0 for an adiabatic process, okay. Are you getting? But if it is less than that, that means it is violating the second law of thermodynamics in this region, right. So, therefore, it cannot really be change in this thing. So, if you look at this side, what will be? This will be 100% what? Reactant, right. This will be 100% product, but in between there will be reactant and product, right, in equilibrium. But keep in mind that if it is a non-adiabatic system, right, then how will handle? We cannot really apply this one, right. So, then how we will handle? We will have to basically look at free energy, Gibbs free energy and Helmholtz free energy, right. And Gibbs free energy, if you look at, that is G is equal to H minus Ts by definition. You might be aware this Gibbs free energy basically thermodynamic potential, one of them is Gibbs free energy. Helmholtz free energy is another thermodynamic potential, right. If I differentiate this thing, what I will get? dG is equal to dH minus TdS S dt, right. Okay. And what is H? H is your enthalpy. Enthalpy is nothing but U plus PV, right. So, if I differentiate that thing, I will get dH is equal to du PdV plus VdP, right. If at a constant temperature and a constant pressure, right, what will happen? Because when we are talking about equilibrium, we will be keeping the pressure constant, temperature constant, otherwise it will be changing, we have seen. So, at constant pressure and temperature, at the constant pressure what will happen? This term will be 0. At constant temperature, this term will be 0. So, if I combine this thing, that means if I say this is equation 1 and this is equation 2 and combine this thing, what I will get? I will get dG is equal to du plus PdV, right, minus TdS. Now, this is from the basically Gibbs free energy. Now, and also you can say second law of thermodynamics. Okay. Now, we will have to connect into the heat, right, because here dq is there. So, from the first law of thermodynamics, we know that dq is equal to du plus PdV. That means this will be nothing but your dq, right. So, therefore, this change in Gibbs free energy is equal to dq minus TdS, right. And according to the second law of thermodynamics, basically dz will be less than equal to 0, right. Keep in mind that change in Gibbs free energy at a constant temperature and pressure, right. Of course, the number of moles are not changing, right. If we are adding some more concentration, as I told, then it will be also changing, less than equal to 0. So, this is the condition under which the equilibrium will be possible, and that means some chemical reaction will be going on, and when it is equal to 0, right. So, that will be the point of equilibrium, right. That means the reaction will attain its chemical equilibrium when Gibbs free energy, or sometimes we call Gibbs function, attains minimum value, that is change in Gibbs free energy is equal to 0. So, that means in this way the reaction will be proceeding, right, but this is not possible like this line, because the second law of thermodynamics being violated, dG is greater than 0, but this is dG is less than 0, right. So, therefore, in this region chemical reaction will be, see if you look at in this region, the reaction, chemical reaction proceeds, right, proceed. This no chemical reaction will be occurring, right. So, basically what we will have to do, we want to find out the equilibrium composition, then we will have to make sure that or use this condition, change in Gibbs free energy is equal to 0 for the mixture, right. Now, if you look at like how we will handle this Gibbs free energy of the mixture, how we will do that? For a mixture of ideal gases, we can determine G of mixture. What is that? Summation of Ni Gi T, right, because there are several mixtures are there, and we are saying okay, sum all those things, that is the mixture. Mixture can be, let us say for example, we have taken hydrogen, oxygen, if we are taking hydrogen oxygen system, hydrogen, oxygen, OH, O, H, right, water, all those things will be coming into pictures, right. And this I can be equal to N, you can say total number of species, whatever it is there, right. And what is this GIT? is the Gibbs free energy for ith species. And this is basically, if you look at, is the total, right, and this we can write down this GIT is equal to GIT corresponding to standard state of the pressure, 1 atmosphere pressure, plus RUT ln Pi divided by P naught, and P naught is basically what? Standard atmospheric pressure, P naught. So, therefore, I can write down G mixture as, right, I can write down here itself, right, Ni bracket GIT naught plus RU ln Pi by P naught, right, and another bracket I will have to put. So, let us say this is your equation 1, right, and keep in mind that this T is whatever the temperature at which we are finding out basically equilibrium, right. RUT, yes, you are right, this T is the and now we need to find out change in the Gibbs free energy of the mixture. That means, we will have to differentiate the equation 1, right. By differentiating equation 1, we can get dG mixture is equal to d, right, of this thing, d of Ni is equal to, if you look at, that is dNi, right, into GIT naught plus RUT ln Pi by P naught, right. First term I have taken Ni and the bracket, then next I will do summation of Ni d this term IT naught plus RU ln Pi by P naught term, right. So, if you look at, let us look at this term, right, second term, this is second term, right, and this is your first term. So, can I say that these will be 0 kind of things? Let us consider second term only, right. That is Ni, I can say dGIT naught, right. I can write down then, oh, I am missing here, T will be there, right, RUT, okay, RUT, I will take it out, then D ln Pi by P naught, okay, and of course, there will be also Ni, right, is that fine? is equal to, if you look at, there will not be any change in the Gibbs free energy, right, there will not be any change, right. So, this will be 0, right. What will happen to this term? This I can write down Ni Ru d ln Pi by P naught, there will be T, okay. So, is equal to, if I look at Ni, right, summation of Ni, right, Ru T, and I can write down this dPi by Pi. Can I write that way? This dP ln Pi, anyway P naught is basically a constant, right, it is not changing. So, ln Pi, if I differentiate, what it will be? Basically it will be dPi, right, by I, and if I sum it, right, if I take Rut, if I take and if I sum this thing, or Rut and then Ni dPi by Pi, right, if I sum it up, what I will get? I will get basically summation of dPi, right, will be d, if I say Pi is basically 0. Can I write this? Because what is happening, you are summing the partial pressure of species is equal to the pressure of the mixture, and that is remaining constant for constant P. This is basically P of mixture, right. So, therefore, it will be 0. Is that clear? So, therefore, this term also is equal to 0. So, that means this term is equal to 0. So, what you will get? You will get dG mixture is equal to dNi, right, GIT0 plus RUT ln Pi by P naught is equal to what? It would be is equal to 0 at equilibrium, at equilibrium. Are you getting? Because what we have done, we have basically looked at that this term is at equilibrium, this is 0. Is that clear? Now, keep in mind that we will have to basically determine this GIT, right. If I will get, then I can also look at it like how we can determine. Let us say this is your equation 2. What we will do? We will now consider a arbitrary reaction whatever we have taken. Let us consider an arbitrary, basically bimolecular reaction A plus B going to the product of C moles of species C and D moles of species D, and A, B, C, D basically B, C, D are stoichiometric coefficients. Right. Now, we will have to basically look at change in species, right. How we will do that? We are interested to find out the equilibrium combustion. We know if you look at equation 2, this is dG mixture equal to dNi into GI T naught plus RUT ln Pi by P naught equal to 0. This condition, that means I have to find out what is this change in the moles of mixture. How I am going to do for this reaction? How I am going to find out this dNi? I will have to basically for this reaction, if I want to write down, what I will have to do? For let us say this is I am saying 3 for above chemical reaction, the Dg mixture will be basically, if I sum it up, what will happen? This will be change in dNA, right, into GA T naught plus RUT ln PA divided by P naught plus RUT ln PB by P naught plus RUT ln partial pressure of C by P naught RUT ln by P naught, right. Keep in mind this will be capital B, this will be okay. Now, how I will have to find out this and all these things I need to know. I will get, for that we will have to invoke law of mass action by using law of mass action for above reaction. What we will get? We will get dNA by A is equal to minus dNB by B is equal to dNC by C dND by D is equal to basically a constant, let us say K. So, now what we will do? We will use this thing here in this expression, let us say this is 4, right. And what I will do? Instead of this, I will write down basically in this place what I will write down? Minus A K, K is your constant, then NB will be in this place minus what? B constant, in this place C constant, this place D constant, right. And then I will rewrite this expression, equation 4, what I will get? I will get, right, and this is equal to what? This is equal to 0, isn't it, at equilibrium. At equilibrium, right, this is equal to 0. And what I will do? I will write down GCT naught plus, is it I am not missing, I am missing something C, right, then D GD T naught minus GA, right. I am doing the same thing, you know, like this is minus is coming, A T naught minus GB T naught, right. and this is nothing but what? Delta G, isn't it? T naught of the mixture, change in Gibbs free energy of the mixture, because all these thing, this is I have done something wrong here, that is A, this will be B, yes or no? And which is equal to what? If you look at, I can take this to the right hand side, right, I will get minus RUT ln PC by P naught, I can write down here PD by P naught divided by PA by P naught P B by P naught. This term we are defining as Kp, right. So, therefore, I can write down this, basically Kp will be equal to E minus delta G T naught divided by RUT. Can I write down? What is the meaning of this thing? If you look at delta G T naught is positive value, what I will be getting? Kp will be less than 1 or not? That means reactants are favored. If delta G T naught is negative value, Kp is greater than 1, reactants are products are favored. Keep in mind that this Kp is a dimensional quantity or non-dimensional? Is it so? It is a non-dimensional quantity, that means it will be unitless. Okay. Kp is a non-dimensional quantity, and Kp, if you look at, is a function of what? Temperature only, it is not a function of pressure. Yes. So, we will stop over here and we will discuss more about this thing in the next lecture, how we can apply this, right, and how all these what we call values we need to calculate. Basically, we will have to learn in the next lecture how we will calculate this value, change in Gibbs free energy, because if I know this thing, right, then I can estimate very easily what is Kp, right. Thank you very much.